So this is Mike and Luke and also Kevin from Blueprint Surf. Kevin sort of are like the big guns for engineering that we call in when we need help with something that we have no idea how to do. Like this, like this. So this is Kevin did some finite element analysis, which is known as FEA, to try to figure out how different 3D printed core structures will perform when we're actually surfing them. And yeah, this is one of the trade-offs that we have for building surfboards in Maine, because we don't always have like waves to push these structures to their limits. But we do have a kick-ass engineer. So we're doing our best. We're using what we have. Yeah, so Kev, can you talk us through sort of how you set up FEA and like yeah, what constraints you use, things like that, how this works?
Sure. So FEA takes a model and cuts it into little structures called a mesh, and then applies a force wherever you define. And it tells you where the stress concentration is. You can see here, there's a little heat map on the right. I can't really make it bigger, but essentially the red areas see the most stress and the blue areas see the least stress. So you're able to find stress risers, areas of stress concentration that might be at a level that would fail the material. So this right now is loaded as ABS plastic, which is pretty similar to the material being used for the surfboard cores currently. And what I did is this is a simple 3-point bending test where we constrained the nose and the tail in these little blocks. The reason we did the blocks was because if you do it just on the tip, it'll focus all the stress right at that area, and you won't really get a good distribution. It would sort of spike the force in that area. So these blocks kind of protrude about 6 inches into the nose and 6 inches into the tail. I kind of show you how the stress is distributed where there's a point load. And then we applied 400 newtons, which is about 100 pounds, to an area sort of representative where your foot would be, and in a similar pattern. And it kind of shows how the model absorbs that stress. So something to note with FEA, there's always going to be stress. So seeing red is not a bad thing, but seeing red in areas that are a potential point of failure is a bad thing. So the stress has to go somewhere. Ideally, it would have a very uniform stress distribution, but that's sort of impossible to do. So you kind of want to look at where the stress is traveling. And you kind of, this is sort of a good example where the center of the strut isn't seeing stress, it's blue, and the force is concentrated on the top and bottom. That's sort of a good thing because you know that you're not sending a stress all the way through the material. So there is an area that's unloaded. That's typically a sign that it won't fail. And you can kind of see here how the stress radiates from the area the force is applied. You see it comes red, then yellow, then green, then blue. So you sort of get a nice, not quite uniform, but a nice kind of long distribution of force instead of a focused distribution of force. So looking at this model, this is our best performing model. It was a diamond pattern that's 3 inches across and 6 inches nose to tail. It had the best stress concentration from the standpoint of the minimum stress at any point is lower than the other models. And you could argue that the highest stress concentration would be the most likely to fail in the same loading conditions as another geometric pattern.
Can you talk a little bit sort of about I mean, like obviously this is an idealized model. Can you talk a little bit about the differences between like these test results and what we might see in an actual board? Like what might be the sources of discrepancies between the test results and
Sure.
what happens?
So it's really hard to simulate something like water, something that is fluid and malleable. This here is basically constraining the nose and the tail and applying a static force. But if anybody who surfs, you definitely know that there's no static force applied to a board because there's always waves kind of pushing and pulling in any direction. your feet are moving around, you're moving. So this is sort of like a snapshot in time if the nose and the tail were loaded, or sorry, were static, meaning fixated, and there's a singular force where your foot would be in the middle of the board, and it's pushing back on the nose and the tail. It's sort of impossible to reproduce this in real life. I don't think you'd ever have a wave holding just the nose and the tail statically. But it's the best we can do, and it gives you information that you could use to compare to other designs, not necessarily predict how it's going to transfer stress in a real world situation.
Yeah, I think also like just because this is just the core structure and it doesn't have any kind of fiberglass skin on it, that's going to have that's going to make a big difference. And we should mention that some graduate engineering students at RU Institute are working on sort of similar modeling, but with the fiberglass in place. That's just like a much more complicated model to run. And
the thing to note when you add fiberglass, that's something that's consistent through all designs. So if you only study the thing that's changing, meaning we have this diamond pattern, we have a square pattern, we have diamond pattern with struts. It's all about comparing apples to apples, where if you add a skin, you're adding an extra variable, but it's the same variable across all designs. So it doesn't really have a tremendous impact on a comparative analysis.
For sure. Yeah. So similarly, like obviously that pad in the middle is not the shape of somebody's heel or the shape of, somebody's foot. But if we just put a foot-sized load right there, it would basically just it just wouldn't simulate very well, right? So we sort of made the place where you're applying the load like a little bit extra big, so it sort of distributes the forces a little bit like like we think the fiberglass would. But yeah, that's a good point, Kev, that
yeah,
as long as we're just comparing structures to other structures, then we hold all of these inconsistencies constant, right? We hold all these sort of like idealized things constant, and it should still be a pretty good comparison.
Right.
Just want to butt in and say that although we're doing the same fiberglass layup of each board, because of how you orientate the weaves, how much resin you have, and there's so many minute details on how each weave like balances on top of itself, that you end up getting slightly different properties for each board. But it's such a hard thing to control that it's not really worth it. Is way more complicated than I think anyone's ever cared to look into. But
I think
that's why occasionally you'll get quote unquote magic boards that just like work really well, and that's when you've got a certain very specific fiberglass like layup that like ends up having the right amount of resin and the right strength and orientation of the weave and everything else.
Yeah. So this is all about, for us, this is all about like acknowledging that this isn't a predictor for how each board is going to work, but it's a pretty good way for us to sort of understand what the different structures can do, right? And what the differences might be.
Yeah, totally.
Definitely.
Sweet. Kev, can you take us through sort of a comparison of the different structures that we looked at, and maybe I'll sort of talk about what we think we're looking for. And maybe if somebody watches this video and they think we should be looking for something different, maybe they can comment and we can do a different study next time. But yeah, basically, what Mike and I discussed, sort of the ways to make a board perform well. You need to have some flex, sort of some way to store and release energy when the surfer is kind of pumping down the line. And most of that, like on a ski or a snowboard, the way those store energy is by bending sort of tip to tail. And then when you come out of the turn, like in a surfboard, so you want it to bend sort of longitudinally, like that diagram we just showed. And then when you release out of the compression of the turn, the board should sort of snap out of that flex position and give you an extra little boost of energy into whatever maneuver you're doing. But at the same time, if you are like going down the line or doing a turn, any kind of torsional flex in the board isn't really gonna, we don't think it's not really gonna help you do that maneuver. It's just gonna kind of be like slop in the board. So, and also probably dissipate some energy. So what we think we're looking for is a structure that can bend tip to tail, but is as rigid as possible in torsion or twisting. Fair?
Great.
Cool.
So I'll walk you through the FEA setup again. So as you can see here, each design was constrained in the same way, loaded the same way. So the nose and tail are constrained. We applied 400 newtons to the center. And with all these outputs, the thing to take note of is we use the same scale. This doesn't necessarily represent what would happen in real life. It just shows that you're comparing all the different designs to the same number pattern or sort of the same color distribution. So these two models were 3-inch squares, one in line with the stringers and perpendicular, and this is a diamond pattern 45 degrees offset. They both perform pretty similar in stress, and then when you get to the diamond pattern, you saw a big improvement in the maximum stress observed at any point in this model. And the reason that's important is when you're considering stress, any sort of stress concentration could lead to a failure. This has nothing really to do with flex and displacement and sort of energy absorption. It just kind of gives you an idea on how different structures compare in the event of like an intense force being applied in one place, which model would perform best in terms of not breaking. So in this case, the 3x6-inch diamond, the model we just saw, had the lowest stress riser, even lower than this other model with stringers going across a diamond pattern. And kind of what we're looking at here, if anybody's interested in the numbers. So this are a maximum force of 3.13 e to the 7th. This was 1.7 e to the 7th. So the stress concentration on this design was about half of what a different design that we use to compare to. So this is say that the diamond pattern shown here has less of a chance of failing under catastrophic load than a different pattern.
So that diamond pattern basically doesn't have, it's basically like an even, it distributes the stress evenly through the structure. Whereas
exactly. Yep.
some of the other patterns like have those little spikes where maybe like something's supporting a lot more of the load than something else. Yeah, like right there, you can see that the stringers are really doing a ton of work. And then next to those bright red areas, the diagonals are like basically blue, right?
Mhm.
Meaning that the diagonals
Exactly.
don't have a lot of stress, but the stringers do.
Right, this is doing a poor job at transferring the stress across the geometry, where the diamond pattern doesn't have that sort of concentration. So you can see here, this is the underside. You see nice uniform colors, there's no red on the underside. That's very important when you're looking at a board from a probability of failure perspective. So two other things we look at are displacement and strain. So displacement is kind of a cool thing. Might be better to show you here. It shows you where the board would flex in a given loading scenario. This is very exaggerated. You'd never see this, but it gives you a good visual of where the displacement would be. So if you're considering, like, would the fiberglass layer sort of like shift or where's the kind of vibration going to be? Displacement gives you like kind of a good indication of that. And again, you'd use this. Go ahead.
I was just going to add, one of the things that's super important about doing FEA on these structures, rather than just sort of like, guessing at what would be stiffer and what wouldn't be stiffer, is like you see how the the rails next to the front foot are actually like warped down, and they almost make like the shape of a Pringle. That like that stuff like that is really hard to predict, how you'll have this complex structure, and if you bend it, like you'd think, oh, we're just bending it nose to tail. It's like hard to imagine, for me at least, maybe other people that's just intuitive, but for me it's hard to imagine that the whole thing like warps into the shape of a Pringle, even if you're just pushing down on the middle of the board and holding the, you know, holding the nose and tail like that.
So yeah, definitely an interesting observation. And real world would be very tough to see this, and you might see failures that you say, hey, why is the fiberglass delaminating from the edge? And maybe there's a little bit more movement there that can be predicted from FEA. So in terms of maximum displacement, looking across the different models, using the same sort of methodology, having the same color scale for each of the 5 designs, taking the max number, the same 3x6" diamond pattern performed best in terms of it had the lowest maximum displacement across all 5. And then thirdly, we look at strain. So this had, again, the same color scale. I can see there's more strain in different areas of the structure around the feet. These all look pretty similar to each other, but the 3x6" diamond pattern also performed best in strain. It saw the least amount of strain in the maximum concentrated area. Any comments, Luke?
No, I mean, it was pretty surprising to me that we found that we saw one structure that was both sort of perform the best in terms of flexing without sort of spiking the stress in one area, and also was able to sort of withstand loads efficiently. You know, it seems like in general, those sort of elongated diamonds are just kind of the best, like just the best performing structure in this kind of in
3-point bending
loading scenario. Yeah.
So having said that, you know, I think it's conclusive that design performs best in loading, but we also want to look at torsion. As this model was set up with constraints on the tail and then a torque applied to the nose. So again, it's idealized, rare that this would happen in real life, but when comparing structures, you can get a good feel on what different torques would look like. So this slide is actually not updated. I pull up the new one. There we go. So this actually showed that the square pattern performs very poorly in torque, where there's a torque applied to the nose. How well does that stress get distributed across the model was, let me put these 2 side by side. There we go. So this is a side-by-side comparison of torque being applied to a square pattern versus the 3x6" triangle. The 3x6" triangle had a much better stress distribution. You can see these entire vertical stringers are loaded in torque, or they're stressed in torque, whereas the diamond pattern had a better stress distribution. And like we talked about before, the center of these diagonal struts is not seeing stress, whereas the entire stringer from top to bottom is being stressed in this square pattern. So this is more likely to fail in torsion than the diamond pattern, just for the sake of comparison, that the stress is more concentrated in the square pattern than the diamond pattern in torsion.
Oh, wow. It's crazy how different they are.
this is the one, this is one of the areas where, and again, one of the things that we talked about is like, once you put fiberglass on this, it's going to be totally different. But for example, like if that core structure with the squares had glass on it, my assumption is that the glass is going to have to do a lot more work to sort of keep it stiff. So it's probably a lot more likely to delam, right? If you have like a super flimsy core in a direction where the board really needs to be stiff, or where their surfer is going to be like pushing the structure a lot. Yeah, so sort of the better we optimize these properties, the better the final board should work, even if it's still a little bit different.
Definitely. So I think that's all the results I had for this analysis. We had some, just looking at where the stress would be in other patterns. It's similar results to the 3-point bending simulation, that the 3x6 diamond, something about it just works better than the others in terms of efficiently distributing the stress.
Cool. Great. Mike, do you have any comments, questions, thoughts on if we're actually like, are we shooting at the right targets to make these boards work well, or?
Yeah, it's really interesting. I'd be curious to see what this would look like with that pattern on the right, but then have one stringer going up the middle of the board. Because in many ways that conventional boards have that stringer, but then also where these rails kind of act as a parabolic stringer in many ways, and they're pretty rigid. But be curious to see what that would look like. And I mean, also just from working with the boards, you can totally tell just by like holding them and moving them around just how different each structure is, and little supports going across the sides, rattle rail versus nose to tail, really matter in how the board just feels before you're glassing it. And obviously to some degree that will carry over to your surfing. But yeah, trying to make sure we don't make the boards too flexible, and then you end up running into like delamination. But then also, you don't want somebody surfing a wet pool noodle instead of a surfboard.
Yeah, I mean, most of the boards that we've made, we've either put one stringer down the middle, or we've put a stringer along each rail.
Yeah.
And I think the stringer along each rail, like that just feels like it should be pretty good. It feels like it's the right answer. But yeah, I think that's something that we need to, keep looking into. And also, obviously, like our goal in the end is to get these under some really, put these through some really aggressive surfing in some solid waves, and get feedback from strong surfers. So cool. Well, Kev, thanks so much for your time and for doing all of this.
Yeah.
And yeah, we will let you know how it goes when we get to push these things out in some larger surf. It'll be super fun.
I'm looking forward to it.
All right, right on. Thanks, guys. Thanks, Mike.
See ya.
Cheers.
Cheers.
Bye.